Hello everyone, welcome to MSc YouTube channel. In this video, I am going to discuss about very important reactions. Every reactions based on stereochemistry, that is known as stereospecific reactions. First stereospecific reactions is Diels-Alder reactions. Let us take the example of the addition of a dienophile to a diene in the Diels-Alder reaction. It is stereospecific. Each geometrical isomer gives us the cis addition product. Butadiene, for example, form adducts with cis and trans cinnamic acids. The configuration of the stereomeric adducts will decide the configuration of the cinnamic acids. This is illustrated by the reaction butadiene with cinnamic acid. This is our butadiene and other reactant which is reacted with butadiene. This is known as cinnamic acid. And gives cis product. Let us take another example for trans product. If butadiene reacts with trans-cinnamic acid, trans-cinnamic acid HPH bonded C, double bond C, single bond COOH, and here hydrogen. Both the reactions, this and this, both are cinnamic acid, but this is cis form and this is trans cinnamic acid. Butadiene reacts with cis cinnamic acid, gives cis product, cyclic product, and butadiene reacts with trans cinnamic acid, gives trans cyclic product. So here gives cyclobutadiene ring, cyclohexene rings, and here phenyl group present, and here carboxylic group present. This is the reaction of, this is the example of Diels-Alder reactions. This is the most important reaction of stereospecific chemistry. There are second stereospecific reactions named as addition of methylene. Let us consider addition of methylenes. This is a stereospecific reactions having each geometrical isomer forms the cis addition product. Thus, it is shown that methylene, also called carbene, from the photolysis of diazomethane added to cis and trans butadiene in a cis manner. Let's take example butadiene, cis butadiene CH3 single bond C, hydrogen, double bond C, CH3, and here one hydrogen. This is cis-but-2-ene. Cis-but-2-ene. Cis-but-2-ene reacts with carbene CH2 with a single lone pair on carbon atom. It attack on this carbon atom and form cis cyclopropane ring. This is the product CH2. This is a carbon and carbon. Here methyl group present and one hydrogen. Here methyl group present and one hydrogen atom. If trans-but-2-ene react with carbene, form trans-cyclic compound. Let's a second example. CH3 single bond, hydrogen, carbon double bond with carbon, and here hydrogen present, and CH3. This is trans-but-2-ene. Trans-but-2-ene. Trans-but-2-ene reacts with carbene CH2 having a lone pair of electron. Lone pair attack this position and form a cyclopropane ring structure CH3 single bond C, here CH2, this is hydrogen, and in this product methyl group present transposition. This is second type of stereospecific reaction. Interestingly, this stereospecificity is lost when the reaction is performed in the presence of an inert gas, that is nitrogen. Each substrate now gives a mixture of the cis and trans products. Methylene formed by the photolysis of ketone added to the above substrates in a non-stereospecific way. So, the stereospecificity of the reaction is due to the addition of singlet methylene, which forms both bonds at the same time. Let's example, alkyl group bonded with carbon, which is carbon double bonded with carbon, and here also present alkyl group. Here hydrogen and here hydrogen atom. It reacts with carbene CH2 having a lone pair. It form it form first intermediate molecule, that is alkyl group carbon single bond and partial bonded with carbon. This is intermediate product formed by the diene and carbene molecule, partially bonded with CH2. This is intermediate complex. Intermediate complex. This intermediate complex is unstable, very unstable. So it transformed into this product. CH2 single bond and here hydrogen atom. This is a cis product formed by the transformation of this intermediate complexes. The non-stereospecific reaction is said to occur due to the addition of methylene in the triplet state. So let's example for non-stereospecific reaction is alkyl group single bond carbon atom, double bond carbon single bond alkyl group R. This is hydrogen and this is hydrogen. Reacts with CH2 having a lone pair. First it gives R single bond C R single bond H and both the carbon atom, one carbon atom bonded with CH2 group and second having single electron, and CH2 have also a single electron. Both are the radical carbon. It transformed into hydrogen single bond carbon and carbon bonded with carbon alkyl group present here. This is hydrogen, this is a alkyl group having radical, and this is a CH2, and both the radicals bonded form a new bond like this. Otherwise it change into this type of product, hydrogen carbon single bond carbon alkyl group CH2 and here the hydrogen and here alkyl group. In this case the radicals present on both the carbon, it form this type of bond and make a circular ring type structure. This is our final product. In the triplet state A and B, this is A and this is a B. In the triplet state A and B, the two electrons have parallel spin and methylene acts as a diradical. The non-stereospecificity is said to be due to the rotation about the single bond, which is more rapid than spin inversion. This is our second stereospecific reaction named as addition of methylene. Our third example of stereospecific reaction will be polar addition of halogen and halogen acid. This is third example of stereospecific reaction named as polar addition of halogens and halogen acids. The addition of these electrophilic reagents is predominantly trans, that is bromine and HCl. Bromine Br2 and HCl. Bromine and HCl. The polar addition of halogen and halogen acid is a two-stage reaction and nucleophilic also. The mechanism is like this: CH2 double bond CH2 reacts with first bromine molecule Br2 single bond Br single bond Br. This is a bromine. In this case, one bromine having partially negative and second partially positive, and this bromine atom act as a electrophile. So the double bond attached with this bromine atom and form CH2 positive ion single bond CH2 Br and form Br minus ion also. Secondly, Br minus attack with this carbon atom and it forms final product CH2 Br single bond CH2 Br dibromoethane. This is our final product, and this reaction is a type of stereospecific reaction named as polar addition of halogen and halogen acid. Second example, ethene reacts with HCl hydrochloric acid CH2 double bond CH2 plus HCl. HCl having H hydrogen have partially positive and chloride ion have partially negative. In this case, this bond attached with hydrogen atom and gives CH2 plus charge single bond CH2Cl and not Cl, it will be CH2H, that means CH3 and Cl minus N. In second step, this chloride ion attach with CH2 carbonium ion and form CH2Cl single bond CH3. This is a second example of polar addition of halogen and halogen acid. In this case, first is this is the polar addition of halogen and this is a polar addition of halogen acid. In case of trans addition, it is suggested that the first step is the formation of a cyclic halogen ion with bromine. It gives the bromium ion first. If a classical carbocation were produced first, then one could expect a free rotation about the newly formed single bond, and therefore in this case the stereochemical addition would not be the one actually observed. Thus, in case of malic acid, the reaction may be written as in this case we take a malic acid, react with bromine, form a intermediate complex. This is a intermediate complex, and this intermediate complex further react with bromide ion Br minus and form cis and trans, cis as well as trans product. Since the bromide ion Br minus can attack with ease only along the Cbr plus charge, that means it attacked this position or this position, and also on the side distant from the bromine. A Walden inversion takes place at the carbon atom attacked. Since the brominium ion is symmetrical, it can be anticipated that either carbon atom will be attacked with equal ease, forming first and second in equal amount. Both are equal amount. This means that malic acid will produce positive and negative plus minus dibromosuccinic acid. So we can write here dibromosuccinic acid. Dibromosuccinic acid. The configuration of the resulting products indicate that trans addition has taken place with the fumarate ion, but cis addition with the malate ion. These results are explained by assuming that the intermediate malate bromium ion. So we can write here this is malleate brominium ion. Malleate brominium ion. The scientist they were suggested that the name of scientist is DAWAR.